In this video, I'm going to talk about circular buffers. Circular buffers are used a lot in audio processing algorithms. They make for quite an efficient way of storing samples and allow us to access delayed samples in the audio stream. If we had an equation like this, what this represents is the current output denoted by this number n. So the n, say, starts at 0, then goes to 1, 2, 3, 4 successive samples. We say that the current output is the addition of the current sample, denoted by x of n, added to x of n minus k, where minus k is a delay in samples of say -6 or -10 or -1000, depending on the algorithm you're implementing. So this could be a fixed value, but it also could be a modulated value. And for example, if we were creating a chorus, this would be the current sample, which would represent, say, the main voice, added to a delayed voice that's modulated in some way. So the important thing is that we store incoming samples, x of n and x of n minus 1, x of n minus 2, that then allows us to tap off the samples to create these different algorithms. If I wanted to, I could add another delay that was twice, if I liked, just by way of example. If we think about data storage, then usually we store things in an array, and this would have location 0 up to this location n. Let's call it capital N because we've used little n previously. And let's say that here we've got index number 9, therefore the size of this array is 10. Okay, so if we stored our first incoming sample, initially x of 0, into this location, then every other sample period we would have to shift x of 0 down to this x of 1 location in order to accommodate a new x of 0 coming in at this point. So this will be xn, x of n minus 1, x of n minus 2, etc. And every single sample period I would have to shift samples, which is really inefficient. So what we can do is we can treat this data as a circular buffer, otherwise known as a ring buffer. And here we have 0, and it goes all the way around to the point where we have 9. And what we do is we write into the first location. So we have a write pointer. So call this write pointer. All this is an index that starts at 0 and just increments around until it gets to 9. Now, what we want to do is, for when we get to 10 and we want it to go back to 0, well, what we can do is we can use a mod instruction. It's this instruction in C, and what this does is modular arithmetic. It will return remainder values. So, for example, if the size of the array is 10, we increment into what we think is location 10. If we do 10 mod 10, then it returns 0, which will point to our first location. Basically, we have a write pointer. We write samples into first location, then we increment the write pointer. So therefore, the next time we write into this location 1, x of n minus 1 is actually pointed here, so that we could say that this is x of n minus 1 location. When we write into the next location, this would become automatically x of n minus 2, x so on and so forth. And we have this ability to write into our circular buffer and index into these delayed samples. And the nice thing, by using this mod instruction, when we get round to the maximum size of the array, it will automatically reset and start writing back into 0 again. And by using this ability, what we're able to do is have multiple tap points. And by using some simple maths, we can say, okay, what is the delay we need? And we can calculate the appropriate value or tap-off point within our circular buffer. Usually when we create one of these circular buffers, we know the size of the buffer that we need. So we would allocate it as a fixed size array in memory. We could, if we wanted to, create a vector, which is sort of a dynamic array, but usually circular buffers are of a fixed size and remain fixed. And that's what we're going to be using in the code that we look at next.